Welcome to RadOnc Smart Review Physics Edition.
Great to be back.
Today we're really digging into how different radiation particles interact with matter, especially with patient tissue. This is super fundamental for understanding dose delivery.
Absolutely. It underlies pretty much everything we do with treatment planning and delivery.
We'll cover how these particles lose energy, how far they penetrate, and some of the, really clinically useful effects that come out of these interactions.
Yeah, this is definitely foundational stuff. Crucial for residents, really at all levels, whether you're gearing up for boards or just wanting to solidify things for clinical practice.
Our goal is to make this stick, make it memorable and applicable.
You know, they say trying to recall the Bragg peak definition on demand after your physics boards is tougher than parallel parking in a crowded city.
Let's hope we can make it stick a bit better than that memory.
We'll give it our best shot.
Okay, let's start with the basics then. Charged particles. Ionization and excitation. We're mostly talking electrons, protons, alpha particles in therapy, right?
Right. Those are the main players. And they're called directly ionizing.
Because they have an electric charge.
Exactly. Electrons are negative, protons and alphas are positive, and that charge lets them interact directly, electrostatically, with the electrons and nuclei in the atoms they pass.
So it's like tiny charged billiard balls, sort of.
Kind of, but the interaction is more field-based. Think
Yeah.
electrostatic forces pulling and pushing on the atomic electrons mainly.
Got it. And these interactions, these collisions, they come in two main flavors.
Yeah. You've got elastic collisions. Think perfect billiard ball hit, kinetic energy is conserved, just redistributed. No energy is really lost to the atom itself.
But that's not where the dose deposition primarily comes from. That's the other type.
Right, the inelastic collisions. That's the dominant way these charged particles lose energy in the therapeutic range. Here, kinetic energy is converted into other forms.
Like excitation or ionization.
Exactly. Inelastic collisions with atomic electrons are the big ones.
So excitation first. That's when the particle gives just enough energy to bump an orbital electron to a higher energy level.
Precisely. The atom gets excited. It doesn't stay that way long. It quickly de-excites, usually giving off a low-energy photon, which basically ends up as heat or light. Not a huge energy loss usually.
But ionization, that's the key for dose. Right?
Definitely. Here, the incoming particle hits an atomic electron with enough energy to knock it completely out of the atom.
Creating an ion pair.
Yep, got it. The positively charged atom left behind, and the freed electron. And that freed electron, if it has enough energy itself, we sometimes call it a delta ray or delta electron, it can go on to cause more ionization or excitation.
So it's a chain reaction, almost.
In a way, yes. This creation of ion pairs is the primary mechanism for how charged particles actually deposit dose in tissue.
Okay, so when we talk about how much ionization is happening along the path, there are specific terms.
Yeah, two key ones here. First is specific ionization, or SI. That's simply the number of ion pairs created per unit of path length. Gives you a measure of how dense the ionization is.
Like ions per millimeter or something.
Exactly. And the second is the W quantity, or W value. That's the average energy you need to spend to create one single ion pair in a specific material.
Oh, right. Like for air, it's around 30-something.
Yeah, pretty standard value for air is about 33 to 34 electron volts needed per ion pair created. It varies a bit by material, but that's a good number to know.
Okay, this leads nicely into probably the most fundamental concept here, LET, linear energy transfer.
Yes, LET. You really need to understand this one. It's defined as the energy deposited locally per unit of path length by the particle.
Locally being the key word there.
Critical distinction. It's not all energy lost, just the energy deposited right there along the track, causing those local ionizations and excitations. Think of it as the particle's drag, or the density of its energy track.
And the units for LET.
Typically, we talk about it in kilo-electron volts per micrometer. Kilo-electron volts per micrometer.
Okay, kilo-electron volts per micrometer. And what determines how high or low the LET is? There's that Beth formula relationship.
Right. Conceptually, the proportionality helps a lot. LET is proportional to Q squared times rho divided by V squared. Let's unpack that.
2 squared first, the particle's charge, squared.
This is huge. LET goes up really fast with charge. So compare an alpha particle, charge plus 2, with a proton, charge plus 1. Same velocity.
Alpha would be 2 squared, so 4 times the LET.
Exactly. 4 times the LET just from the charge difference, assuming the same speed. Big impact.
Then there's rho, the density of the medium. Makes sense, denser stuff, more atoms to hit.
Yep. More interactions per unit length, so higher LET in denser materials like bone compared to water or air.
And finally, the crucial one, v squared, velocity squared in the denominator. So it's
Yeah.
inversely proportional.
This is the key to understanding things like the Bragg peak. Faster particles have lower LET. Why? Because they zip past atoms so quickly, there's less time for that electrostatic interaction to occur.
Less dwell time near each atom.
Precisely. And the flip side is really important. As a charged particle travels through matter, it collides, loses energy.
It slows down.
And as its velocity v decreases, that 1 over v squared term means its LET goes up. Dramatically so, especially near the end of its path.
Okay, so if we compare particles with similar starting energies, alpha particles are heavy and doubly charged, so high LET protons are lighter, singly charged, so intermediate LET, and fast electrons are very light, singly charged, and fast, so low LET.
That's the general hierarchy, yeah. Alpha high, proton intermediate, fast electron low. And you can roughly relate LET to specific ionization too. LET is approximately Si times that W value we mentioned.
We should probably also mention the continuous slowing down approximation, the CSDA.
Good point. For these charged particles, especially protons and alphas, we often model their energy loss as a continuous process, losing small amounts of energy in frequent collisions, mainly with outer shell electrons. It's an approximation. Things like Bremsstrahlung happen for electrons where they lose a big chunk of energy at once. But CSDA gives a good overall picture for how they gradually slow down and stop. Which brings us to range. Since they are continuously losing energy, they eventually stop. They don't go on forever. The total distance they penetrate before coming to rest is their range.
And the range depends on?
Primarily initial energy and average LET. Higher energy means more fuel in the tank, travels further. Higher average LET means it's losing energy faster per unit distance, so it stops sooner.
Yeah.
You could roughly say range is kind of like initial energy divided by the average LET.
Now, for electrons, there's that incredibly useful clinical rule of thumb for range in water or tissue.
Ah, yes, the workhorse rule. You absolutely need to know this. The practical range in centimeters is approximately equal to the initial electron energy in mega electron volts divided by 2, range in centimeters, energy in mega electron volts 2.
Let's say that again because it's so important. Range in centimeters is roughly energy in mega electron volts divided by 2.
Memorize it. Use it daily.
Yeah.
You need to treat to, say, 3 centimeters deep with electrons. You need roughly 2 times 3, so a 6 MeV beam, mega electron volts.
Perfect example. A 10 MeV electron beam gives you about 5 centimeters range. Mega electron volts, centimeters. So useful for selecting energies for superficial targets.
Couldn't do electron plenty without it.
Okay, now for the heavy charged particles, protons, alphas, carbon ions, we see something really unique at the end of their range.
Yes, the famous Bragg peak. It's quite remarkable, really. Instead of the dose just gradually falling off, you get this sharp, intense peak of dose deposited right near the very end of the particle's path.
And then after that peak,
The dose just plummets,
Yeah.
drops off incredibly rapidly to almost zero.
And the reason for this sharp peak goes right back to LET.
Directly back to it.
Yeah.
Remember, LET is proportional to 1 over velocity squared. As the proton, or alpha, gets near the end of its range, it has lost most of its energy, so its velocity is very low.
Low velocity means
Sky-high LET. It starts dumping energy much more rapidly per unit distance traveled right before it stops. That intense energy deposition rate creates the Bragg peak.
I like the sprinter analogy you mentioned earlier. Runs fast most of the race, fairly low energy expenditure per step, maybe.
Right, lower LET.
But then that final burst at the finish line, massive energy expenditure right before collapsing.
That's the Bragg peak. High LET right before stopping.
So give us an example range for a clinical proton beam.
Sure, a 250 MeV proton beam, mega electron volt, might have a range of, say, roughly 28 centimeters in water. Centimeters. But the vast majority of that dose isn't spread evenly. It's concentrated in that sharp Bragg peak just before the 28 centimeter mark. Very little dose goes beyond it.
Huge clinical advantage, obviously. Okay, let's completely switch gears now. Neutrons.
The neutral ones, big difference.
Key difference. No electrical charge, so they're indirectly ionizing.
Exactly. They don't interact via electrostatic forces with electrons like charged particles do. A neutron has to physically hit or get very close to an atomic nucleus.
And then what happens?
Well, that nuclear interaction sets charged particles in motion, things like recoil protons. And those charged particles then go on to cause the ionization and excitation that deposits dose.
Because they don't interact continuously via charge, they can travel further. They're quite penetrating.
Generally, yes. They don't feel that constant electrical drag, so they can penetrate quite deeply until they happen to have one of those nuclear interactions.
So what are the main ways neutrons interact with nuclei, especially in tissue?
Okay, several types. First is elastic scattering. Think billiard balls again.
Yeah.
Neutron hits a nucleus, bounces off. Kinetic energy is conserved overall, but transferred.
And this is important for...
Very important for fast neutrons interacting with hydrogen in tissue. Tissue is full of hydrogen, right? Water, fats, proteins. A hydrogen nucleus is just a proton.
Right.
When a fast neutron hits a proton, similar mass, it can transfer a large fraction of its energy to the proton. Knocking it forward is a recoil proton.
And that recoil proton is charged.
Yes, and it's often quite energetic initially, but because it's a proton, it has a relatively high LET, depositing its dose densely over a short range. This is the main way fast neutrons deposit dose in tissue. Scattering off heavier nuclei, like carbon or oxygen, transfers much less energy.
Okay, elastic scattering producing recoil protons. What else?
Inelastic scattering. Here, the neutron is briefly absorbed by the nucleus, excites it, and then the nucleus kicks out a neutron again, but one with lower energy than the original. Usually, a gamma ray is also emitted as the nucleus de-excites.
Then there's transmutation. Sounds like alchemy.
Sort of. The neutron is absorbed, and the resulting nucleus is unstable, so it ejects a different particle, like a proton or alpha particle, actually changing the element. A classic example is neutron plus nitrogen-14 gives carbon-14 plus a proton.
Interesting. And what about slow neutrons?
For slow or thermal neutrons, the most important interaction in tissue is radiative capture. The slow neutron gets captured by a nucleus, most commonly hydrogen again.
Hydrogen 1 captures a neutron, becomes hydrogen 2, deuterium.
Exactly. It forms an excited state of deuterium-2. This excited nucleus then immediately decays by emitting a gamma ray. So the reaction is neutron plus hydrogen 1 yields deuterium-2 plus a gamma ray. Neutron plus hydrogen 1 and deuterium-2 plus gamma ray. That gamma ray then deposits dose. This is really significant for thermal neutron dose in tissue.
And fission, neutron splitting heavy nuclei.
Happens, but not really relevant for dose depositions in the patient during typical radiotherapy. More relevant inside a reactor or bomb.
Okay, so let's summarize neutrons in tissue again. It's mostly hydrogen doing the interacting.
Pretty much. For fast neutrons, the main story is elastic scattering off hydrogen, creating those high LET recoil protons.
And for slow or thermal neutrons.
The main story is radiative capture by hydrogen, releasing gamma rays.
Got it. And you mentioned neutron penetration increases with energy, but they might not be as skin-sparing as high-energy photons.
Right, because even high-energy neutrons can undergo these scattering events near the surface, creating recoil protons right away, which can increase the surface dose compared to the buildup effect you see with high-energy photons.
Okay, we've covered a lot of the physics mechanisms. Let's bring it back to the clinic.
Right.
Why is understanding all this detail, LET, Bragg peaks, neutron interactions, so critical for radiation oncology practice?
Oh, it's fundamental. First off, LET and RBE, relative biological effectiveness. They are directly linked.
Because high LET radiation causes denser ionization tracks.
Exactly. Think about those recoil protons from neutrons, or the protons and alphas right at the Bragg peak. They leave a really dense trail of damage as they pass through a cell.
More damage in a smaller space.
Right. And that dense damage is much harder for the cell to repair properly. You get more complex DNA damage, like multiple double-strand breaks clustered together. That's why high LET radiation is generally more biologically effective per unit of absorbed dose.
So neutrons and protons typically have an RBE greater than 1 compared to photons or electrons.
Generally, yes. The exact value depends on many factors, but the principle holds. Higher LET often means higher RBE, LET, RB.
And the Bragg peak itself, that's the whole physical basis for proton therapy's main advantage, isn't it?
Absolutely. That ability to dump the vast majority of the dose in a sharp peak right at the target depth with minimal dose beyond it. That's what allows proton therapy to deliver highly conformal dose to the tumor while potentially sparing critical normal tissues located distally or downstream from the target. A huge physical win over photons which have an exit dose.
And then there's the electron range rule we hammered on earlier.
Can't emphasize it enough. Range in centimeters equals energy in MeV divided by 2. Centimeters, mega electron volts. You use this every single day you plan an electron treatment to pick the right energy to cover your superficial target. Maybe a chest wall, maybe some nodes, while minimizing goes to the lung or heart underneath. It's basic, but essential.
Finally, neutron interactions. They explain both neutron therapy and why shielding neutrons is such a headache.
Right. Neutron therapy, which isn't common but exists, tries to leverage the high RBE of those recoil protons, especially for tumors thought to be resistant to conventional photon therapy. But neutrons are tricky.
Because they're penetrating and interact in complex ways.
Exactly. Shielding them effectively requires a combination approach. You need hydrogenous materials, concrete, water, polyethylene plastic to slow down the fast neutrons via elastic scattering. Then you need materials with a high cross-section for capturing thermal neutrons, like boron or cadmium, to absorb the slowed-down ones.
But the capture often produces gamma rays.
Right. So you also need high Z material, like lead, to attenuate those captured gamma rays. It's a multi-step process. And remembering that neutrons can actually be produced in a regular linear accelerator if the energy is above about 10 MeV, megavolts, through photodisintegration in the head, that's absolutely critical for designing the shielding of the treatment vault itself.
Wow, okay. Lots of clinical connections there. Let's try to distill this into some really high-yield clinical pearls, stuff you absolutely need to remember.
Sounds good. Let's crystallize the key takeaways.
Okay, pearl number 1, LET definition and what it depends on.
Right. Linear energy transfer, LET. Local energy deposited per unit path length. Remember the key proportionality. Proportional to charge squared, inversely proportional to velocity squared. And the comparison, alpha proton electron for LET at similar energies velocity.
Pearl 2, the Bragg peak.
Yeah, that sharp dose peak near the end of the range for heavy charged particles like protons and alphas, caused by that dramatic increase in LET as the particle slows down to a crawl.
Pearl 3, the electron range rule, your clinical go-to.
Absolutely. Practical range in centimeters is approximately initial electron energy in mega electron volts divided by 2. In water or tissue, centimeters, mega electron volts.
And Pearl 4, how neutrons interact in tissue.
2 main modes to remember. Fast neutrons primarily via elastic scattering with hydrogen, making high LET recoil protons. Slow thermal neutrons primarily via radiative capture with hydrogen, releasing gamma rays.
Excellent pearls. Ready for a quick board blitz to test ourselves?
Let's do it. Fire away.
Question 1. Order the following particles by increasing linear energy transfer, LET, from lowest to highest, assuming they have similar initial velocities. A, alpha proton electron. B, electron proton alpha. C, proton electron alpha. D, electron alpha proton.
Okay, increasing LET velocity is similar. LET depends mainly on charge squared. Electron charge is 1, proton is 1, alpha is 2. So electron and proton are lower than alpha. Between electron and proton at the same velocity, the much lighter electron is generally considered lower LET in this context, though it's complex. But alpha is definitely highest. So electron, then proton, then alpha. That's B.
B is correct. Rationale. LET increases significantly with charge squared. Alpha charge plus 2, proton plus 1, electron plus 1.
Got it.
Question 2. The characteristic peak of dose deposition that occurs near the end of a proton's path in matter is called the A Compton edge. B penumbra. C Bragg peak. D isodose curve.
That's got to be C, the Bragg peak.
Correct. C Bragg peak.
Okay.
It describes that sharp increase in dose deposition at the end of a heavy charged particle's range due to the increasing LET as it slows down.
Makes sense.
Question 3. You need to treat a target volume where the deepest edge is at 4 centimeters depth in tissue. Using the practical electron range rule, what approximate electron beam energy should you select to ensure adequate coverage? A. 4 MeVB. 6 MeVC. 8 MeVD. 9 MeV, or the next cynically available higher energy. Centimeters. MeEV.
Okay, rule is range in centimeters equals energy in MeV divided by 2. Centimeters, mega electron volts. We need range 4 centimeters.
Yeah.
So energy in MeV is approximately 2 times range in centimeters, mega electron volts, centimeters. 2 times 4 equals 8. 2 times 4, which equals 8. So we need about 8 MeV mega electron volts. Clinically, you want the therapeutic isodose, like 80 or 90%, to cover that depth. And that line is usually a bit shallower than the practical range. You typically choose the calculated energy or more likely the next available energy up to be safe. So D9 MeV or the next higher one available, mega electron.
Exactly right. Answer is D. Walk through the calculation perfectly. Energy L, a 2x range equals 2 by 4 centimeters equals 8 MeV. Clinically, select 8 MeV or the next higher energy, like 9 MeV, for adequate isodose coverage. Centimeters, mega electron volts.
Good rule to practice.
Last one, question 4. Fast neutrons primarily deposit dose in tissue via which mechanism? A. Radiative capture with hydrogen, releasing gamma rays. B. Elastic scattering with hydrogen nuclei, producing recoil protons. C. Inelastic scattering with oxygen releasing alpha particles, D-pair production near carbon nuclei, creating electron-positron pairs.
Okay, fast neutrons in tissue, hydrogen. That's the billiard ball collision with protons. Elastic scattering producing recoil protons. So B.
Correct again. B, elastic scattering with hydrogen is the dominant interaction for fast neutrons in hydrogenous materials, creating those high LET, ALE recoil protons that deliver the dose. Radiative capture is for slow neutrons.
Phew, okay, blitz complete.
Nicely done. So let's just quickly recap the absolute main points from today's session. We started by distinguishing between directly ionizing particles, the charged ones like electrons and protons, and indirectly ionizing ones like neutrons.
Yep. Then we dove into linear energy transfer, LET. Defined it as local energy deposition per unit path length. Saw how it depends on charge squared and inverse velocity squared, leading to that general hierarchy. Alpha proton electron, LET.
We discussed range, how far particles travel, and spent time on that vital clinical rule. Electron range in centimeters is about energy in mega-electron volts divided by 2 centimeters mega-electron volts. And of course, the unique Bragg peak for protons and other heavy charged particles, driven by that increasing LET at the end of their path.
And finally, we covered the key neutron interactions in tissue. Fast neutrons mainly cause elastic scattering off hydrogen, making high LET recoil protons, while slow neutrons mainly undergo radiative capture with hydrogen, releasing gamma rays. We tied all this physics back to clinical realities like RBE, the rationale for proton therapy, how we choose electron energies, and the basics of neutron therapy and shielding challenges.
It really shows how understanding these fundamental particle interactions is essential for everything we do. It makes you think, especially with the Bragg peak, how perfectly can we sculpt that dose? Is there always some lower dose noise from secondary particles or range straggling, or could we theoretically get even sharper dose fall off?
That's a fantastic question, always pushing the envelope of physics and biology. What are the ultimate limits? Something to ponder.
Definitely. Well, for our listeners, you can find notes and continue discussion on all this.
And next time, in P4, we'll actually step back and look at how some of this radiation is generated, specifically focusing on kilovoltage X-rays produced in X-ray tubes, which conveniently involves electron interactions with target materials building right on today's concepts. Kilovoltage.
Perfect segue.
For complete practice oral boards, check out radonsmartlearn.com, or pronounced, radonsmartlearn.com, and be sure to subscribe to Radiation Oncology Smart Review for our next session. Thanks for tuning in.
Thanks, everyone.